title of my talk is Pinning Down Privacy in Statistical Databases. And as the title suggests, a lot of the talk is going to be about discussing the meaning of the word in quotes and how we convert this sort of natural language notion into something more mathematically rigorous. So when I say privacy in this talk, I'll be talking about privacy in statistical databases. What I mean by that, imagine you've got a bunch of individuals who have sensitive data, personal data of some kind, that's collected by some server or agency. And the goal of the server or agency is to make the benefits of this data available to as wide a public as possible. So they'd like it to make it available to users. They'd like users to be able to ask queries about this data. But they're concerned about the privacy of the information that's in that data set. So, large collections of sensitive personal information are actually ubiquitous. Census data is the classic example, but of course there are lots of other good examples. Things like clinical and public health data, data gathered from social networks, both the online kind and the traditional offline kind. Recommendation systems, trace data from computer systems like search records, network usage, that kind of thing, data collected by intrusion detection systems. So recently there's been a trend towards more and more types of data being collected. So these data sets are getting both larger and a lot more varied and a lot more valuable. And so they're valuable both in the sense that they offer, mining this information offers all sorts of public benefits. But when we, by and large, consider it a sort of social good that things like clinical data be made as available as possible. But there's obviously this flip side to it that we need to be concerned about the information that's contained, the sensitive information contained in these data sets. All right, so we basically have two conflicting goals. On one hand, we want to get as much utility out of these data sets as we can. On the other hand, we'd like information that's sort of specific to individuals, whatever that means, to remain hidden. So the theme of the first at least half of this tutorial, more like 2/3, is going to be how can we define this question precisely, and what are the challenges involved in formalizing it? Okay. So variations on this model have been studied for a long time in statistics under the name statistical disclosure control since the 60s and 70s, in the data mining and database communities since the early 80s, where it's come to be called privacy-preserving data mining, although that term has a second very distinct meaning in this community that I'll get back to in a couple of minutes. But roughly since 2002, there's been a push from several communities, although it started very much in the crypto community, to try and put this field on more rigorous foundations. And so I'll be telling you a little bit about that. Okay, so why, what are the differences between, privacy as I mean it in this tutorial and crypto? One of the challenges that in privacy, there are no bright lines. Okay, so whereas in crypto, we're used to a situation which is roughly follows the model of the psychiatrist with the patient, where there's some sensitive information. There's a group of people who are supposed to have unrestricted access to that information, namely the patient and the psychiatrist himself or herself. And then there's sort of the rest of the world, and the rest of the world should have absolutely no access to that information. It should be completely hidden from them. Okay. What I'll try to explain is that actually with data privacy, we don't get these bright lines, and we sort of have to pick and choose what we're going to release. When we release certain types of information, we do so at the expense of other kinds of information. And moreover, if we wanted to have the kind of strong types of guarantees we get in the crypto we're all used to, then we wouldn't be able to release anything at all. Okay, so that's one big difference. And in particular, it's very different from secure function evaluation, what's sometimes meant by privacy-preserving data mining. If you hear it in this community, in particular a talk at Crypto 2000, that introduced the term. So, secure function evaluation roughly focuses on how to securely distribute a computation that we've already agreed on. Okay? Whereas in the question in data privacy is which computation should we actually be distributing? And I'll give you some examples later of how starkly those two questions can differ. So maybe another, the companion question to ask is how can crypto contribute to this field of data privacy? I actually think crypto has a lot to say, in particular about, as a community, we think a lot about modeling security and what it should mean, and how different measures of information leakage and things like that. We're sort of used to thinking adversarially, and I think that's a contribution that our community can make to this area is sort of, more hacking, and just thinking about different kinds of attacks, so both carrying them out and also kind of trying to establish a systematic understanding of them. And thinking about what the various security and privacy concerns are in various distributed models, something I won't really get into today, but I think is a very interesting topic. What can crypto get out of it? Well, as I'll try to convince you that privacy has this aspect to it that we're sort of forced to deal with non-negligible leakage of information. And so one of the interesting aspects of it is that it kind of pushes us into coming up with a theory of how to think about these sort of moderately secure settings. And these are things that come up to some extent already in crypto, but I think this is sort of a different twist on that. And I think some of the ideas that are being developed in this area will have applications to other areas that are sort of more traditional crypto, like anonymous communication systems and voting, perhaps, and things like that. All right. Okay, so this is a tutorial. You might hope that this will be an overview of research on this sort of broad question I've laid out. Unfortunately, data privacy research is extremely diverse. It involves researchers from lots of areas, which makes it fun. It involves tools from lots of areas, which also makes it fun and challenging. Unfortunately, that also means it's very hard to cover in a 75-minute tutorial in any kind of with any kind of real coverage. And so, necessarily, I had to pick and choose, and yeah, deal. All right. The other thing I wanted to say is, there's been a lot of progress in this field since 2002. We really are 10 years ahead of where we were in 2002. But the area is still immature, and that also makes it hard to give a tutorial because it makes it hard to present the sort of really coherent theory of everything that one would like to give. And so I hope you'll forgive me for not doing that, and I hope you'll view it as sort of a challenge and an interesting one to kind of participate in making it a bit more mature. Okay, so this talk, it's more tutorial than survey. I'm going to try to go in depth into a couple of things rather than touching on everything. There's a lot of stuff that's been left out, as I said. I will be discussing my own work a reasonable amount, but I won't only be discussing my own work. I'm sorry about that. And then just a disclaimer that my slides are somewhat sparse on references because there were just too many to fit, and so they should not be. If I've left your work out on some slides, I apologize ahead of time. And one last disclaimer: no Hitler cats. Sorry. All right. Okay. So this talk, an outline. First act, we'll talk about attacks, and I'll be getting into the math of reconstruction attacks in particular, but really, in some sense, the purpose of this first section of the talk is to explain why the problem is hard. Okay. Act 2, definitions. I'll go into depth about one particular approach to sort of pinning down this ambiguous notion of privacy called differential privacy, something I was involved in developing. And I'll be talking about variations on the theme of differential privacy, and also some of the things that are good about it, and some of the flaws it has, or not flaws per se, but some of the things that one would hope to remedy about it. And then I'll be talking, sort of third part, I'll be talking about algorithms for designing differentially private algorithms. I'll get through some basic techniques such as noise addition, exponential sampling, and then I've got some more advanced stuff that I may or may not have time to get to. All right. So what's the deal with attacks? So one of the things that makes this problem hard to reason about and quite different from the settings that we're used to as cryptographers is that there's these users that are getting access to the information, but they themselves have access to lots of external sources of information. They could get information from the internet, from their own social networks, maybe other anonymized data sets. There's all sorts of other information about these individuals out there other than what's coming out of the server or the agency. Okay. And we can't really assume we know what those sources are. But unfortunately, in a sense that we'll make precise, we can't ignore them either. The way we can somehow in traditional crypto with auxiliary information, we can almost forget about it. The definitions are so strong that we don't really have to think. We've found ways to kind of not think too hard about auxiliary information. As a result of these complications, anonymization schemes are really regularly broken, or things that people thought were anonymous are regularly broken. So I'll start up with a warm-up, some examples of problems that have gone on with anonymization systems, and then I'll talk in a bit more detail about reconstruction attacks. Okay, so one example is the Netflix data release. Many of you have probably heard about this. In 2006, Netflix released a data set to help with, for the purposes of a competition on recommendation systems. And what they released were, so Netflix is a movie rental company. They released ratings for a subset of movies and users. So their users and movies those people had watched. So for each usernames they removed the usernames. They were replaced with random IDs. There was some additional perturbation added, although that wasn't entirely specified. And then basically, so for each of these users, you got this random ID together with a list of movies they'd reviewed, or a subset of the movies they'd reviewed, rather, and the scores they'd given and an approximate date of the review. Okay, and what Arvind Narayanan and Vitaly Shmadikov did at Texas was to take this anonymous data and correlate it with an external source of information. In this case, they looked at the public data available through the website IMDb, which is a movie ratings website, where what people can do is create an account, normally with their real name, and post reviews of the movies they want everybody to know they watched, and how much they like them. And these are the movies that they actually watched, all the movies they watched. And what they were able to show that it wasn't not too difficult to actually re-identify the records on the left based on this sort of very partial and incomplete information available on the right. And in fact, on average, it took about 4 movies to uniquely identify a user. And really, as a result of this work and the publicity it created, the second round of the Netflix competition, which was meant to take place in, I guess, 2010 or so, was postponed basically indefinitely. All right, so that's one example. I guess one thing about this example, it illustrates the perils of very high-dimensional data. So this data set is very sparse, right? Most people don't watch actually a large fraction of the Netflix movie corpus. So it's hard to condense this data set into some smaller, more succinct format, and that was part of the issue. Another type of issue that can come up, this is something from my own work, is something I'll call composition attacks, which should be a name that's natural for this crowd, especially given the session we just listened to. And this is an example. You've got 2 hospitals that serve overlapping populations, and what happens if they independently anonymize and release data about the populations they serve? Okay. So it turns out that if you that you can actually combine these these releases to learn a lot about the people who are in the intersection of these populations. Okay? If for various popular anonymization schemes, including k-anonymity and L-diversity and a few other things. The idea is really not that complicated. Roughly speaking, there's a sort of a large class of anonymization schemes that were around for a while, pre-2002 in particular, where the kinds of information that were released, what you'd learn about, if I was the person in the intersection, what you'd learn about me would say that I visited the hospital either because I had diabetes or for complaints about high blood pressure. What you might learn from the other hospital database is that I visited for one of some other set of possible reasons, and under the reasonable hypothesis that the two visits that the two visits happened around the same time, then you could look at the intersection of these sort of disease lists, and actually typically the intersection is a single item, and you figure out what the problem is. Okay, you figure out why I was visiting these hospitals. There are lots of other attacks out there in the literature. I'm not going to go through them from a bunch of various domains. One of them that bears mentioning is this paper of Homer et al. That appeared in the genetics community on genome-wide association data. And basically, that paper caused the NIH, the National Institutes of Health, to pull a whole bunch of data off of their websites, and it sort of drastically changed the policies in the genetic community for sharing research data. Okay, so these are some attacks. One might ask, what's going on? What's wrong here? So let's try and sort of understand a little more in a little more detail. So far, the examples I gave you all had to do with releasing individual information, and so one might ask if that's what's going on. That the problem is that the information that's being released is just too fine-grained, and that if we just release sort of coarse-grained global statistics about the data, we'll be fine. Okay, and actually, we won't, and there are a few reasons for that. So one of them is, again, composition-type problems. So suppose I tell you the average salary in a department before and after a given professor resigns, then you learn exactly how much that person was making at the time they resigned, right? Incidentally, this illustrates the difference, one of the differences why, let's say, secure function evaluation is sort of addressing a different problem. So secure function evaluation would tell you how to release the average, but it doesn't tell you whether or not releasing the average is a good idea. Also, seemingly global results, even in a one-shot version, can reveal all sorts of specific values. So there's a popular classification algorithm called a support vector machine. It produces a linear classifier, so it's sort of a rule for telling apart two different kinds of points in a data set. Roughly, it's just a line in space or a hyperplane. And it's derived through some relatively complicated algorithm, but the description of the final output is always given in terms of a very small number of actual exact input points in the data set. So even though it's the result of sort of this very global processing, the final output actually reveals a bunch of data points in the clear. Maybe a more subtle problem is that global statistics taken jointly may together encode a lot of information about data. And the attacks that take advantage of this are often called reconstruction attacks, because they sort of reconstruct some piece of data based on a bunch of released information. And roughly, what these reconstruction attacks, they all have the same broad flavor, is that if you release too accurate statistics, then you can reconstruct either the entire data set or some very particular part of it. And these reconstruction attacks are robust even to fairly significant noise, and I'll tell you a little bit about those. Okay, so as I intend them, these sort of came up first in this paper of Dinur and Nissim in 2003. Let's make things a bit more concrete. So suppose we've got some data set X, and we want to release this function f of x, or some approximation to it. Okay? And then essentially a reconstruction attack is going to take this approximation to f of x and reconstruct some x hat that's ideally close to x. So to make it more concrete, imagine we've got n users. Each one has a secret bit. And the types of queries we're going to allow are going to be subset queries. So for a given subset of the data, what I'll ask for are, the query I'll ask is to tell me the sum of the bits in that subset, or rather divided by 1 over n for convenience. Okay, so I can think of this as sort of an inner product of the characteristic distribution vector of my set S with this vector of secret bits, and then I just add, I divide that by n, so it's normalized between 0 and 1. Okay, so the question is, what sets of subset queries, what collections of subset queries allow me to reconstruct, say, significant parts of the data? And so I might ask, how many queries can I make before I start running into trouble? How close is my reconstruction of the data to my original data set? I'll use Hamming distance to measure that. And also, how much noise does my algorithm tolerate? So if I've got a certain amount of distortion in my answers, how well do I do in terms of reconstructing the data? And also, how much time does the attack take? Okay, so I'll give you, there's a lot of work on this. I'll give you sort of two data points. One was the original paper of Dinur from the original paper of Dinur and Nissim. So they give an attack that uses sort of 2 to the n queries, so all possible queries. It gives something with, if the queries are reconstructed within distance are accurate to within alpha, then the reconstructed data set is correct on all but an alpha n fraction of the points, basically. Okay, so if alpha is, basically if alpha is little o 1, if alpha is very small, then I'm reconstructing the data set exactly. Okay? And the algorithm is very simple. The idea is that if I've got some candidate data set y that I think might be my real data set, I can just write the Hamming distance between y and x in terms of 2 subset queries. Okay, this S1 and S0, where S1 is the set of positions in which y is 1, and S0 is the set of positions in which y is 0. And basically, if I'm given approximations to all of these subset queries, then I can just get an estimate for this Hamming distance in terms of, by using the estimate I have for fs1 of x, the estimate I have for s0 of x, and I just output the data set that minimizes this estimated distance. Okay, so it's a very simple attack. Takes a long time, right? You're basically explicitly searching over the entire space. But at least it tells you can't release everything, at least modulo running time considerations. You can't release everything at high accuracy, at even any non-trivial accuracy, and not basically broadcast your data. Right? There's a sort of various refinements of that result. I'll give you another data point on there. So one is, instead of using to the n queries, I use n queries, and the number of the error to which I reconstruct now is higher by a factor of square root of n than it was before. But now my running time is significantly better. It went from 2 to the n down to basically linear. So this attack is meaningful when the noise is little o of about 1 over square root of n. Okay, that's when it's basically reconstructing the entire data set. And one can show that's optimal. Okay, and I can explain the attack to you. It's very elegant. This is a version from a paper of Dwork and Yechaning at Crypto 2008, actually. I want to construct this sort of subset of queries to ask. What I'll do is I'll choose my queries according to the rows of a Hadamard matrix. So this is a +1, -1 matrix. So the entries are +1 and -1. It's defined recursively by this pair of formulas. And a Hadamard matrix has the nice property that all of the rows, any 2 rows of the matrix differ in exactly n over 2 positions. Okay? And because they're +1, -1 matrices, that means the inner product of any 2 rows is exactly 0. So the matrix is orthogonal, and that tells you that all its eigenvalues are actually exactly plus or minus square root of n. Okay, so we know a lot about this matrix. All right, and now what I'll do is, it turns out that using n subset queries, roughly 1 per row, I can reconstruct something like the matrix product of this Hadamard matrix with the secret data x. Okay, so there's a little mismatch here. I'm talking about plus 1 minus 1 matrices, and I said my queries were 0, 1. Turns out that's easy to deal with. And my what my error guarantee tells me is that I'm getting something. I'm getting this matrix product plus an error vector e, and I know something about the L infinity vector of e, the L infinity norm of e. It's at most 2 alpha in this case. Okay, and now what I can do is I can compute an estimate for x hat, an estimate x hat for x. I'll call it x hat prime because afterwards I'm going to have to round it. So x hat prime, I'll just take the inverse of this matrix. So I invert the Hadamard matrix. I multiply by n to take care of that 1 over n thing. And I multiply whatever I reconstructed, this information z, by the inverse of this matrix. And obviously, what I get back is x, since Hn is invertible. I get back x plus some other error vector e prime, which is just e multiplied by this inverse of the Hadamard matrix. And because I've sort of controlled the eigenvalues of the Hadamard matrix, I know exactly how much the length of E can be blown up by. And that allows me to analyze this rounding procedure in this sort of very simple way and figure out that if the error is below 1 over square root of n, then again, x hat will agree with x in almost all the positions. OK, so these attacks that I've just described, they can be extended considerably. They can handle some very distorted queries. They can exploit sparsity in the error vector. So I won't tell you too much about it. Maybe I'll just mention that these results draw on this sort of deep and extensive theory of reconstruction from the signal processing world. And there are really nice connections to things like compressed sensing, if these are things you've heard about. It's a very nice area to play around in. OK, so far from the examples I've given you, the queries are kind of very unnatural in the sense that they were kind of algebraically defined, which is kind of odd. Or it turns out you could also use uniformly random queries. And the other kind of funny thing about the queries I've described is that they somehow require you to be able to name rows, to talk about, oh, give me the sum of these specific, give me the bits of this specific set of people. Okay, and it may not be a priori obvious why that's possible. So you could ask, could you pull this off with sort of natural, very symmetric queries that don't have this feature of name, the kinds of things people actually release about, say, government data sets or clinical data? And the answer is yes. Okay, it turns out that the same ideas can be exploited, say, to get reconstruction based on releases of marginal tables, for example, regression analysis, decision tree classifiers, a bunch of other things. Okay? So basically, once you start releasing too much information that's too accurate of almost any kind of information about your data, you're going to run into trouble. I won't explain the details since I want to move on to other things. But maybe I'll just sort of summarize what I wanted to say about attacks. So far in the literature, there are a lot of ad hoc examples of attacks. There are some general principles starting to emerge, things like composition properties that we'd like, but not too much there. There are some very sophisticated attacks out there. These reconstruction attacks are examples. They draw on the theory of coding and signal processing. And there are some sophisticated lower bounds for various classes of release mechanisms, sometimes using ideas from crypto, like based on the hardness of forging various signature schemes, that also are quite sophisticated. But I would say, by and large, we still don't have anything like a systematic understanding of the picture of what kinds of attacks are possible. There's no kind of clean taxonomy or anything like that. And there's certainly nothing close to a suite of standard attack techniques the way we have, say, for the design of block ciphers. Okay? And I think this is something the crypto community could help with. OK, so just transitioning to the next part of the talk, what have we learned? Well, even if we're releasing only aggregate statistics, we can't release everything. Okay? When we do release information, some information, that means we're releasing it at the expense of other kinds of information. Okay? And this kind of inherent trade-off is actually very different from from crypto as usual. Okay, we're used to kind of this nice hybrid arguments that say, well, if each of my blocks has not negligible leakage, then I can run them a bunch of times, and the leakage doesn't add up too much. But here it does, right? Okay, even a single aggregate statistic can be hard to reason about. The support vector machine example I gave, I think, illustrates that. And really, it sort of begs the question, what exactly does aggregate mean? Okay? And so that's kind of where we're going with the definitions, is to try and understand that question. So having shown you some things that can go wrong, it'd be nice to try and understand, well, you know, what would it mean for things to go right? At this point, so that's going to be the sort of second third of the talk. You know, maybe it's good to sort of take a break and stretch, at least for me. I should say this is a tutorial in a rather formal setting, so I realize it's somewhat hard to ask questions during a tutorial when it's like, you know, you and 200 of your closest friends. But feel free to ask questions if you'd like to. Okay, so let me tell you about definitions. So what I'd like to do is I'm going to start off with sort of one approach to defining privacy in this context, called differential privacy. And then I'll talk about some of the good things and bad things about it and other approaches that are out there. Okay, so the high-level idea with differential privacy is that we're going to try to define aggregate. The meaning of aggregate information is information that's stable to small changes in the input. It should be able to, it's a definition that handles arbitrary external information in a sense that I'll define precisely. And it's a burgeoning field of research. There's really a lot of work going on there now. And I'll tell you about some of that in the third part. Okay, so the intuition is that I'm going to try to define privacy in the following way. Changes to my data, meaning a particular person's data, should somehow not be noticeable to users on the outside of the system. Okay, and what we'd like to enforce, really, is that in some sense the output is independent of any individual's data. Okay, although that's a more problematic interpretation. Okay, so formally, here's the picture. We've got this data set, x1 through xn. Each of the entries in my data set could be come from some domain. This domain can be arbitrarily complicated. It could be numbers. Could be categories. It could be, you know, your tax forms. It could be some complicated high-dimensional summary of your data. We're going to think of x as fixed, not random. But there is randomness involved. I'm going to think of the algorithm A as a randomized procedure. And in particular, for every fixed x, A of x is a random variable. And that randomness might come from adding noise. It might come from resampling or all sorts of things like that. Okay. And what we'd like to do is compare the behavior of this algorithm on an input x to its behavior on a neighboring data set, where a neighbor is a data set that differs in one data point from x. Okay. There are actually several ways to define exactly what differing in one data point means. And I'm not going to get into the distinctions between those, but for today, just imagine that I take, you know, person 2's data and I replace it with some other thing. So the intuition behind the definition is that neighboring data sets should somehow induce close distributions on outputs. Okay, so this is very much inspired by indistinguishability type definitions in crypto. And specifically, we'll say that A is epsilon differentially private if for every pair of neighbors x and x prime, for all subsets of possible outputs, so for all events in the probability space, the probability that A of x lies in this output, in this set of outputs, should be approximately the same as the probability that it would land in that set under x prime, up to this multiplicative factor of e to the epsilon. So think of that as sort of 1 plus epsilon if epsilon is reasonably small. Okay. All right, so you know, this really is a metric on probability distributions, by the way. If I use the smallest possible epsilon there, I get this is actually a metric on distributions. And so this is really saying that neighboring data sets induce close distributions on outputs. Okay, so one thing to notice is condition on the actual algorithm. It doesn't talk about a particular output, a particular table being safe to release. And that's very natural, I think, in our community, but it was actually sort of a big deal at the time for this area. Okay, so a lot of previous definitions had this flavor. One thing I will say is that the exact choice of distance measure matters. It matters a lot in terms of how meaningful the definition is. And I'll talk more about that in a minute. And then the obvious question is, well, what's this, epsilon here? So it's some measure of information leakage. But it's not too small, unfortunately. I think maybe 1 in 10 or 1 in 100 or 1 in 300, but not 1 in 2 to the 50 or something like that. Okay, and I'll talk more about this in a few minutes. Let me go through an example of something that satisfies this definition first. Okay. So suppose I've got this function f, some function f that I'd like to release, and I'll think of this function as it's just some vector-valued function that returns a vector of p real numbers. Okay. And what I'd like to do is I'd like to add some kind of noise to f and then just release that noisy estimate. Okay. So for example, I might be interested in releasing, I might have a data set, a clinical data set, and I might be interested in releasing the proportion of diabetics. Right? So that for each person I have a bit, and the f of x I want is just 1 over n times the sum of these bits. So a simple approach is to add noise. The question is how much noise? And the intuition is, well, we should be able to satisfy this type of indistinguishability definition as long as f itself is insensitive to changes in the entries of x. Okay. So this leads us to this definition. We'll say the global sensitivity of f is the maximum change I can get from f of x to f of x prime for neighboring data sets x and x prime. So for example, pictorially we've got here x and x prime. We've got a little ball around x of radius 1. And I'm curious, how big is the ball around f of x, the corresponding ball around f of x? Okay, so for example, for the proportion, the change is at most 1 over n. And what you can prove is that if you add noise proportional to this global sensitivity of f in each of the entries, so remember this f could be a vector, then that algorithm is epsilon differentially private as long as the noise has to scale like the global sensitivity divided by epsilon, and it should be distributed according to this particular Laplace distribution, which is kind of like a Gaussian distribution but a little pointier, and its tails go down linearly with the magnitude of the argument instead of quadratically. Okay, so this is a distribution with standard deviation, well, roughly this argument. Okay? So you're adding noise proportional to this quantity. And the reason it worked, the reason it's differentially private is that if I consider two different data sets, x and x prime, then what I'm doing is I'm considering two Laplace distributions centered at different values, f of x and f of x prime. And so essentially I'm just comparing a translated version of this density function with itself. And it turns out that the Laplace distribution has the property that when you shift it by a certain amount delta, then the change in the probability of any given event scales as e to the delta. Okay, so it just sort of matches directly the definition we wanted. So for example, for the proportion of diabetics, we're releasing the proportion plus or minus 1 over epsilon n. So you might ask, so this is we're releasing this approximately, right? This is a random variable with whose absolute value is about this big. You might ask, is this a lot of noise? So it's some amount of noise. Is this a lot of noise? Is this a little noise? Well, it does go to 0 with n. That's sort of a good thing. But more precisely, if x is a random sample from some large underlying population, then the sampling noise, just the sampling noise, the fact that I'm not looking at the actual population but some sample from it, is going to be on the order of 1 over square root of n. So the error I get just for basic statistical considerations is going to be on this order. And so the noise I'm adding for privacy is less than that, considerably less than that for large n, right? So this goes to 0 much more quickly than this quantity. And so what that means is that this quantity a of x is essentially as good as the real proportion, at least for statistical inference. So in as much as you want to know about some underlying population, then this amount of noise is not getting in the way. Right? So that's some crude way of calibrating. You know, are we distorting things too much, too little? Okay. So it turns out this global sensitivity, what's come to be called the Laplace mechanism, because you're adding Laplace noise, has been very useful. And that's because a lot of natural functions have low global sensitivity in this sense. So for example, if I've got a histogram, I'll come back to that. So a histogram of a data set that has constant global sensitivity, the mean, sample mean, covariance matrix, things like the distance to a given property, having the data, how many points do I have to change for the data set to satisfy a given property, various things that people do in statistics and convex optimization. Okay? And so there are a lot of things that kind of naturally just drop into this framework. And moreover, this mechanism can be thought of as a programming interface where I can imagine what I'll just do is I'll just ask for various functions, make different queries where my query describes a function. What I get back is the answer to the query, right? Some noisy answer to the query. And indeed, a lot of algorithms that don't themselves have low global sensitivity, if you think of them as sort of talking interactively to the data, then the questions they ask of the data do actually have low global sensitivity. So for example, and there are a number of papers on this, but a good example of this is a k-means clustering algorithm. I'm not going to go into it because it would take too much time. But the k-means clustering algorithm has this property that it all of the individual updates made by this iterative algorithm have very low global sensitivity. And so what you can do is add noise sort of inside the algorithm instead of to the final output. And that actually works pretty well. This idea was actually implemented in several systems, first of all by McSherry and something called Pink, and later by a few other people. And I will come back to those and talk more about them at the end of the talk. Okay. So this is, let's see, this is more for the TCC crowd in the audience, but let's just hack away at the definition a bit. So what is this definition really telling us? Okay, so first some notes. As I said earlier, epsilon can't be too small. Okay? It's actually easy to see why that is. If I consider two data sets that are as far away as possible, they have Hamming distance n, okay, then just by the triangle inequality, if my algorithm satisfies this definition, those two data sets will be at distance at most n times epsilon. Okay, so if epsilon is small, then these two data sets induce very close distribution. If epsilon is, cryptographically small, these two data sets are so close that you're not getting in, you can't tell them apart. And so it's just totally useless. Right? So these are exactly the kind of things we want to be able to tell apart. The other thing is, why this funny distance measure? Why can't we use something more traditional, like statistical total variation distance, KL, something like that, mutual information maybe? And there are good reasons for that. So let me just consider as a straw man a mechanism that what it does, it takes my data, and so let's say the U.S. Census corpus, right? It grabs one person at random and publishes that person's data in its entirety. So it turns out that mechanism satisfies the following property. For any two data sets that differ in one person's data, the statistical difference between the induced distributions is actually exactly 1 over n. Right? And that's because the chances that you're the unlucky person are very small. Right? They're only 1 over n. But of course, with probability 1, somebody gets shafted. And so we kind of need some distance measure that's a little more worst case, that is more sensitive to this type of problem. Okay, and that's why we settled on this definition in the original paper. Some other nice things about this, it satisfies the natural composition lemma. If A1 and A2 are epsilon differentially private, then the joint output, A1, A2, is itself 2 epsilon differentially private. Okay? And so you get this kind of graceful degradation as you compose systems, just like you'd expect in an indistinguishability-based definition. The difference here, of course, is that 2 epsilon is really much bigger than epsilon, because epsilon isn't that small. Okay? So these things accumulate quickly. And the other thing that's nice about this definition, before I start telling you all the things that aren't nice about it, is that it actually remains meaningful in the presence of arbitrary external information. Okay. Let me explain what I mean by that, because that's a claim that's often misunderstood. All right. So we're in the line of work of trying to interpret the definition. It would be nice to have something along the lines of what we have with, say, semantic security of encryption, where we could say that if you're the adversary who's looking at the outputs of the system, your beliefs about me are the same after you see the output as they were before you saw the output, right? So you've really learned nothing about me. Okay? Unfortunately, that's very hard to achieve. Okay? So consider the following example. Suppose as side information about me, you find out that I smoke. Okay? And suppose that you then read a public health study, the anonymized results of a public health study, that teach you that that there's this sort of strong link between smoking and certain kinds of lung cancer and throat cancer. Okay? So you could then from that learn that I myself am at risk for cancer, in particular that I'm a bad insurance risk, right? Okay, so in fact, you've learned a lot about me. If you didn't know this, if you lived on a different planet and didn't know that smoking was problematic, and you read this, public health study, then you could figure out that, you'd learn a lot about me, right? And in fact, that's exactly what we want, right? That's exactly what these studies are supposed to do. They're supposed to teach us about, connections between, sort of high-level connections between different attributes of people. And notice that what you learned about me didn't actually matter whether or not my data was used in this public health study. Right? You learned something about me even though I may have gone nowhere near the person doing the survey. Okay. So this was formalized first by Dworkin Noor and sort of reformalized by Kiefer and Machanavachala recently. And it's not hard to argue that learning things about individuals is sort of unavoidable in the presence of interesting external information. Okay? And there's this sort of a couple of theorems out there proving this, but actually the smoking and cancer study pretty much tells you the whole story there. Okay. So what can we say? So we can't get a guarantee like this. What you can say about differential privacy is that no matter what you know ahead of time, you'll learn almost the same things about me whether or not my data is used in the calculation of the statistics. Okay. So it's not that you won't learn about me. You should learn things about me, but what you learn shouldn't depend on the use of my data. Okay, and you can sort of formulate this in this nice Bayesian way in terms of how an adversary updates a prior distribution about me, say. Okay, but at a high level, I think the English sentence conveys it well. All right, so these are the reasons that I like the definition, and some of the reasons the definition has caught on and become, I think, a focus of a lot of study. And what I wanted to do was tell you in a couple of minutes some of the caveats that come with the definition, and I think that highlight again why privacy is sort of a tricky area, and we don't necessarily have the sort of silver bullets that we have in the sort of area of traditional crypto. Yeah, Ben, you had a question.
Just the definition relies on a clean definition of what my data is.
That's right. Well, we'll get there. Yeah. Okay. Let me put that on ice for about 3 bullets. Okay. So So one of the interesting things about the definition is it provides a formalization, maybe not the only one, of a line between kind of global and individual information, right? But it does, what happens when the global information is itself the problem, right? So, the smoking and cancer situation, if I'm denied health insurance because, some pesky doctor went out and did a study about smoking and cancer, I may not be happy, right? More serious example that if I've got a data set of financial transactions, differential privacy might provide privacy for individual investors' actions, but it might not hide say, trading strategies that are used at the level of a large financial institution. Okay, because those are that's sort of a global piece of information that concerns lots of people. There are lots of settings, for example, in the context of social networks or data about relationships, where my presence in the data actually affects everybody else, right? So this gets to Ben's question, is that if you've got, say, data about a social network, it's very difficult to pin down which part of that information is just about me, okay? As a trivial example of that, consider what I call the annoying colleague example. Suppose that let's consider a hypothetical situation that I've got a colleague who every time this person shows up for a faculty meeting, everybody leaves annoyed, okay? I don't actually have such a colleague, I'm happy to say. But suppose I were to do a survey of people before and after this faculty meeting, okay? I could easily figure out, even if the results were differentially privately protected, I could easily figure out whether or not that person had showed up at the meeting. Okay, just by virtue of everybody being pissed off. And so, when the data is about people who actually react together, then it becomes much harder to say what's my data, what's your data, right? And I would say that was nicely pointed out in this sort of paper of Kiefer and Much and Avachala last year. And they had another example in the same paper where they were looking at what happens if I've got exact deterministic information about this data set that somehow comes from another source. How can I use that? So for example, this is sort of a simplistic example, but suppose I'm trying to release the populations of all 50 states, and what somehow gets released through a side channel for whatever reason are the exact differences between the populations of all those states. Okay? So now, I might release something that turns out there is a differentially private release, which would allow you to figure out the exact populations of all the 50 states with very high confidence based on this side information. Okay? So even though there's no, without this side information, it's hard to figure that out from a differentially private release. With this side information, whether or not my data is used, you could figure this out exactly. Okay, because you've got this sort of side channel, this very, very kind of brittle side channel. All right. Another type of issue that comes up is that leakage accumulates. These epsilons, they add up with lots of releases, and they're really inevitable in some form or other. And so the obvious question is, how do we set epsilon? And I'm not going to say anything about that. So this type of issue is inherent in the problem, but it's not clear that the particular trade-off, the particular formalization provided by differential privacy is the right one. Okay, so there are a lot of variations on this idea that are out there, and I'll just mention a few of them as food for thought. So one is first there were some predecessors to this definition. I've been bad about giving citations so far, so I'm not going to change that now. There's something called epsilon delta differential privacy, which is a relaxation where I add this additive delta. It's got very similar semantics as long as the delta is very small, which it normally is. There are various variants that incorporate computational considerations from the adversary's point of view, like bounded running time on the adversary in various ways. And there are distributional variants where what I'll do is I'll try to assume something specific about the adversary's prior knowledge, maybe a prior distribution the adversary has, and I'll try to exploit that to perhaps get a deterministic release rather than something that's randomized. So there are a couple of papers on this. There was a paper at AsiaCrypt last year in particular that made a lot of headway in formalizing this. But one thing that comes with these deterministic releases is they almost necessarily have poor composition guarantees. So it's tricky, and there are a number of papers on that. And there are various generalizations of this definition that are kind of simulation-based. One of them from TCC last year called zero knowledge privacy. The other called distributional privacy, which is sort of confusing. I'm not going to talk more about this zero-knowledge privacy paper here because it's going to come up in a talk tomorrow, or I think it's tomorrow or Thursday. But it's out there. It's a strict strengthening of differential privacy. And then there's something called pufferfish, which came out this year, which is a sort of a generalization of differential privacy, a very vast generalization where you've got lots of knobs that you can turn, and differential privacy is one of the things you can get out of it. It's an interesting paper. The problem with vast generality is it then becomes very tricky to instantiate. Suddenly you have to make all these choices, and it gets complicated fast. Okay, and then there's another work on cloud blending privacy that I'm not going to talk about because, again, there's a talk on that tomorrow. All right, so so what did I want to say about these variations? So there are a lot of variations out there, and I think that perhaps this one's not interesting just because it's very similar to epsilon differential privacy. It's not that it's not interesting, but it doesn't really change the semantics. The computational variants change things in the distributed setting, but not so much in the single server setting. The distributional variants are perhaps the place where there's a lot of insights to be made still, where we really have a very poor idea of the right way to incorporate precise assumptions about adversarial knowledge here. Okay, and I think there's sort of interesting open questions there of what's the right way to do that. Okay, so we've got this definition. Privacy will equate now to the fact that changes in one input should lead to small changes in the overall distribution. And then the question becomes, well, what computational tasks can we achieve privately? Okay. So there's been there's been a lot of work on this, and we've developed a lot of tools for reasoning about differential privacy that I hope will be valuable sort of more broadly in this space. And it's just there's a ton of interesting work. I mean, it's impossible to survey, but just to give you an idea of the communities in which it happens, there's the StoxFox Soda crowd, the database people and data mining people, the sort of Usenix and security crowd, the learning people, us, and the networking folks, the statisticians. So this sort of work on this topic has been published in a lot of different venues. And as I said, that makes it very difficult to survey, but it also makes it an interesting area to work in. Okay, and so what I'd like to do with my remaining time, which isn't as much as I'd hoped, is to tell you more about how to design differentially private algorithms and some of the cool results. Okay, so again, let's just sort of take a second to stretch. If you want to stand up and stretch, you can do so, because it'll become a lot more technical fast. As one person said, I will now switch into Yevgeny Dodus mode and start pressing the clicker button a lot faster. Okay. Okay. So, all right. So what we're after is sort of an understanding of what do we know about designing differentially private algorithms. Okay. Well, we have some basic tools and techniques. So I mentioned the Laplace mechanism. There's something called the exponential mechanism that I will describe. There are various algorithms for answering a vast set of queries simultaneously or in sequence where there's some sort of basic techniques that have been developed there. There's a set of techniques that revolve around the idea of local sensitivity that I might get to. There's a lot of work on sort of basic theoretical foundations, feasibility results about learning or optimization or synthetic data, connections to game theory, learning robustness. There are a lot of domain-specific algorithms for, say, network data or clinical data. And there are a number of systems that were implemented, and I'll talk about them right at the end. Okay, so I want to talk about tools and techniques. So my goal here is to give you enough information that if you go and try to read papers on the topic, it'll be easier. Okay, so technique number one is noise addition, and by noise addition I mean the simplest variant, which is the Laplace mechanism. That's what I talked about earlier. So this is just the same slides as before, just to remind you. Just to give you an example of where this can be useful, suppose I've got a histogram. So suppose I've got my data points lie in some domain. I don't know what the domain is, but I've somehow partitioned it into a bunch of disjoint bins. okay, maybe the 50 states. Then I could consider the following function, which counts how many data points live in each of the bins. Okay. And now, if I add or remove one person from the data set, then at most one of these numbers changes, right? And so the global sensitivity of this function is 1, even though independent of the dimensionality. And so it's sufficient to add noise to get differential privacy. It's sufficient to add noise on the order of 1 over epsilon, so essentially a constant, to each of these counts, and you get something differentially private. And again, regardless of the dimensionality. So you get something that scales very nicely to very high dimensional outputs. And it's going to be very useful as long as the bins aren't too sparsely populated. If there are a lot of zeros and ones in this counts, then you're kind of obliterating that information. Okay, so an example of this is a histogram on the line. There are some nice results on the convergence of density estimators based on this idea. The populations of 50 states I just mentioned. The marginal tables that I mentioned briefly earlier are an example of this. And so, there are some various algorithms for releasing marginal tables based on this that are fairly accurate. I'm not going to tell you the details. There are variants of this noise addition idea that in other metrics. So I talked about, I defined global sensitivity. Maybe I didn't make it precise in terms of L1 noise. It turns out you can generalize this in various ways. For example, you can use L2 to measure the distance between functional outputs. And there are cases where that makes a huge difference. And basically, the theorems get a bit more complicated. You have to add normal noise, Gaussian noise. The parameters get messier, but they still have that global sensitivity over epsilon plus a bit, plus some other stuff. And then the guarantee changes. It's now epsilon differentially private instead of epsilon 0. For example, if I've got a bunch of predicates I want to know, say subset queries, a large set of them, then what I can get, if I've got d of them, then I can add noise proportional to square root of d to each of these questions and get something differentially private for subset queries. And that actually matches the reconstruction attack lower bounds that I mentioned earlier for some settings of parameters. Okay, so that's one basic technique, the Laplace mechanism. It comes up a lot. The other very basic technique is something called exponential sampling, or the exponential mechanism. That came from a paper of McSherry and Talwar. And their motivation really was that sometimes noise addition just doesn't make sense. Okay, so for example, suppose what I'm trying to release is the mode of a distribution on a discrete data set, right? So what does it mean? I want to know, are more people voting Republican or Democrat? I can't add noise to Republican, right? It doesn't make sense. I could consider something complicated like the minimum cut in a graph. Right? What does it mean to add noise to the description of a minimum cut? Or some classification rule given by like a decision tree or something like that. Again, it's hard to add noise to that. So their motivation was sort of this broad class of problems. Specifically, they were looking at auction design problems. Because differential privacy has this lovely property that it also implies approximate truthfulness of an auction. If an auction is differentially private, it is in some sense a truthful auction. And that has generated a line of work connecting differential privacy and game theory that is the subject of a whole other tutorial. So this idea that was first applied for auction design subsequently came to be applied very broadly. So let me give you an example. Suppose I'll call this a voting example. It's not really voting. Suppose I've got the following data. I've got a bunch of students at UCSB, and they've visited various websites today. And I might be curious to know what was the most visited website today. Okay. So I've got the data lies in some range, which is the set of possible website names. Okay. And for each person, I've got a set of websites. Okay, so for each possible website, let me compute a score, and the score is just the number of students who visited that website. Okay, so my goal is to output the most frequently visited site, or at least some approximation to that. And the mechanism is the following: given my data set, I'm gonna sample the name of a website from a funny probability distribution that depends on x, and that probability distribution will assign probability to y, which is proportional to e to the epsilon times its score. Okay, so that's a funny probability distribution, right? So here's the green is the score. The blue is this sort of exponential version of this. So the idea is that, why is this a reasonable thing to do? Well, popular sites are exponentially more likely than unpopular ones, so hopefully I'll get something good out. On the other hand, why does it have a hope of satisfying privacy? Well, one person's data changes the website score, all the website scores by at most 1. And so the sort of individual probabilities in this distribution won't go up or down by too much. Okay, so more formally, here's my mechanism again. The mechanism, as stated, is 2 epsilon differentially private. And that's because if I consider the ratio of the probability of y under x to the probability of y under x prime, I really got two ratios. There's the thing to which I want to be proportional and the constant of proportionality, this normalization factor. And each of those kicks in a factor of at most e to the epsilon, and I get this e to the 2 epsilon. Okay. So now for utility, the claim is that if the most popular website has score t, then what I'm going to get in expectation, I'm going to get something whose score is almost t. So it's going to be t minus, something that is the log of the number of websites. So if we're talking a couple of thousand websites, it's not that big, over epsilon. And remember, t here is the number of students who visited the most popular website. So presumably it's a large number. And the proof is just a line, but I'm not going to do it. All right. So what's an example? Let me give you another. So that's voting is one example. But it turns out it's a special case of something much more general. I could have a set of outputs y with some prior distribution p of y. And as long I just need any score function such that for neighboring data sets x and x prime, the difference in scores is at most 1. Okay? Or it just has to be bounded, because I can always renormalize the scores. And then I do this. I output an element from my set of possible outputs with probability that scales as the prior times this factor of e to the epsilon q. Sorry, there's an extra minus sign there. There shouldn't be. E to the epsilon q. So I want things with high score to come out more often. Okay. So now, for example, let me give you an example. Suppose I've got a set of, suppose I'm trying to learn a classification rule for a data set. I might have a set of possible classifiers that I'm considering. Those could be, decision trees, or they could be settings of the parameters for some, linear classifier. For convenience, I'm going to work with discrete objects. So let's think of it as maybe a set of discretized half-planes. Then my score could just simply be the error rate of this classifier on the data. So how well does it do at distinguishing, good credit risks from bad credit risks, or whatever the data set happens to be. I'm going to add a minus sign because I want to select for things with high score, not low score. And now it turns out that just by the same analysis I didn't give you on the previous slide, the output, I get a classifier whose expected error rate is the rate of the optimal classifier plus some number that scales as the log of the number of classifiers divided by n. So as long as the number of classifiers grows more slowly than e to the n, then I'm in good shape. Okay, I get something with vanishing additional error. Okay, and a corollary of this came from a Fox 2008 paper, is that every pack-learnable concept class, if you know what pack learning is privately pack-learnable. Okay, so the mechanism above is extremely general. In fact, it's completely general. Every differentially private algorithm is an instance of that mechanism. Okay, so that makes it sort of threateningly general. It's almost too general to be useful. It turns out, though, it's still a really useful way to think about designing algorithms, and that perspective was used explicitly to design algorithms for a bunch of different contexts. So we've got these two basic techniques in our toolbox, right? Noise addition, exponential sampling. If you remember nothing else from this talk other than those two techniques, you'll actually have a pretty good basis for reading papers on this topic. I'd like to give you an application to releasing a whole list of functions that sort of nicely combines these two techniques together with some other stuff that I'll explain. Okay, so this is the last thing I'll get to. Imagine we've got a bunch. So we're going to consider something called linear queries. So these are sort of related to subset queries, but sort of not. And so I'm going to redefine everything just to be totally clear that we're all on the same page. I've got some data set X, which is a multiset in some domain D. Okay? So it's OK. Different people can have the same value. That's OK. And I'm going to think of the vector. I'm going to think of X as a vector in R to the D, which has been normalized so that the entries sum to 1. So it's actually I'm going to think of my data as a probability distribution over the domain. Okay, so the ith entry of this vector is the number of occurrences of I in X divided by n, the number of people. And what's a linear query? A linear query is just a function from the domain to 0, 1. And what my answer, the answer to the query f on data set X is the expected value of that function over this probability distribution X. Okay, so it's just the sum. Sorry, it's 1 over n times the sum over the multiset of the values of the function, which is the same thing as this inner product. I can write f as a vector, x as a vector, and I get an inner product. Okay? Sorry, there's a 1 over n missing right where the pointer is. So subset queries that we talked about earlier are special cases of that, as long as you represent things just the right way. And most of the low sensitivity queries that people actually use fall into this category of linear queries. Okay. And our goal is that given a bunch of queries, F1 through Fm, we'd like to release approximations F1 hat through Fm hat. And what we're aiming to minimize is the maximum possible error we would have made. Okay, so the worst difference between the true value and the approximated value. And the question is, how low can I get this error to be? Okay? So we could use the Laplace mechanism. Right? Sorry, this is just our error measure again. We could use the Laplace mechanism plus some basic composition results to get error that scales as, so m is the number of questions I'm asking. So the error scales as m over epsilon n, or if you fiddle with things a little bit and use that Gaussian noise thing I mentioned earlier, you can get square root of m over epsilon n with this additional delta. But in any case, it's only useful, either way, this mechanism is only useful when the number of questions you want to ask is relatively small compared to the size of the data. So it has to be much less than m over n squared, than n squared. But the good thing about it is it runs reasonably quickly. I mean, you can implement it. Okay. All right, so we might ask, well, maybe, is this the best possible thing we can do differentially privately? It's actually complicated. So the answer is yes, in certain settings of parameters, when n is very large relative to m, or even just a bit bigger than m, then you can show that this is optimal. This mechanism is optimal in general. But in the interesting range, when this mechanism fails, that is, when the number of queries is very large, it's really not clear what happens. Because those reconstruction attacks we talked about earlier, they only rule out a certain amount of error. They rule out error 1 over square root of n, but they don't rule out all possible error. Okay? And in fact, there's reconstruction attacks can't, because if I just randomly sample people from the population and publish that, then I'll give you something that allows you to estimate any linear query within about error 1 over square root of t. Okay, log m over square root of t. And so if I were willing to publish a bunch of people's data raw, then I'd be fine. Okay, I'd get actually a pretty useful mechanism. Of course, I don't want to do that, because that means those two people get completely screwed. All right. What's surprising was there's this line of work that started a pioneering paper of Blum, Liggett, and Roth, and that generated a lot of interesting follow-up. And they showed roughly I can get error that scales much more nicely in terms of the number of questions I want to ask. I can actually get logarithmic scaling in the number of questions. I pay an extra factor, which is log of the size of the domain, the number of different data values I can get. And instead of things scaling with 1 over n, they now scale with 1 over n to the 1/3, or 1 over n to the, oops, that's a typo. That should be a half. 1 over square root of n, maybe. But the point is, the great thing about this is it's useful when m is very large. The bad thing is that it goes really slowly. That is, you pay running time proportional to the number of possible elements in the domain. So that could be very large. let me try to give you, in a minute, a quick overview of how these ideas work. So I'm going to give you a version due to Hart, Liggett, and McSherry, and it's based on an idea of kind of what I'll call learning the data that came out of a paper of Dworknauer, Reingold, Roth, and Vadan. So what I'm going to do is I'm going to design my algorithm this way. Hidden inside my algorithm, I'm going to have somebody who's trying to learn X. But he talks to X through this very restricted interface of being able to use either the Laplace mechanism or the exponential mechanism to ask questions. All right, so the release mechanism tries to learn X through this differentially private interface, and he's going to output a synthetic data set, a data set X hat, which hopefully minimizes this error, which is the sort of difference on these queries between X hat and X. Okay. Note, in general, I'm not actually reconstructing X here. I'm just reconstructing it relative to this very specific measure. Okay. So it's kind of weird to think about it as learning because there's this, but the correspondence holds up remarkably well. So whereas before, what in learning would be thought of as the parameters of some linear classifier I'm trying to learn, that's now the data set. Okay? And what used to be the data, those are going to become the queries. And what used to be gradient computations in the sort of most of the algorithms people use for classification are going to become actual data accesses. Okay? So why is this even remotely reasonable? Well, the way it's going to work, the learner is going to compute a sequence of estimates to the data set. And if I look at my current error on my current estimate, and I look at the gradient of that error, it turns out the gradient of that error, if you sort of just work through it, it's exactly, it's up to a minus sign, it's exactly the function fj that maximizes, that makes us achieve this maximum. Okay? So the basic idea for the algorithm is at each step, I'm going to use the exponential mechanism to try and find the query that's causing my current maximum error. And I'm going to use the Laplace mechanism to ask, well, what exactly is the difference between, which direction is the error going in? Am I too big or too small right now? And then I'll do some wacky-looking update based on this, which isn't all that wacky. It's a classic idea that comes from the multiplicative. It's called the multiplicative weights mechanism. It's a classic idea. And then I'll sort of do this kind of wacky exponent. It's actually an update. I'm doing gradient updates on the log of the x vector instead of the x vector itself, which is sort of confusing, but there are good reasons to do this. Okay, and basically I'll just give you the utility claim in a second. Is that if I do it right, then I've got some potential function, which is the Kullback-Leibler distance between x and my current estimate x hat, and that thing drops by the square of the current, roughly the square of the current error on each iteration of this algorithm. Okay. So why is it useful to have the KL distance drop? I actually don't care if the KL distance goes to 0. That's not that's not my utility function. All I'm using this is to measure. I'm using this to measure progress of my error in some other way, because as long as my error is large, then this utility claim tells me I will make an update that reduces the potential a lot. Okay, but the potential it doesn't start that large. It starts at log d, and so if my error is always above alpha, then after log d over alpha squared steps updates, I will run out of updates to make. I will run out of potential to use up. And so what that tells me is that actually this algorithm will, after this many updates, it will be giving you an x hat that has error less than alpha, proportional to log d over 1 over alpha squared. Okay? And that's kind of really, I think it's a remarkable analysis. Basically, given the analysis on this slide, you can work out all the parameters, those parameters I had on that previous slide. Okay, at this point, I will skip to the end of the talk. So I wanted to tell you about how to take advantage of local sensitivity-based methods, but I also kind of knew I wasn't going to get there, so I'm not too disappointed. All right, so let me just end with a quick postscript about systems and implementation. So this talk has been sort of very theoretically focused, as you probably noticed. but what's going on in practice? There's a lot actually going on in practice. The high-level message is so far, differentially private algorithms are, there's been a lot of progress, but they're still hard to use. Okay, they're hard to use because they add noise and distortion, and that's something that users of data don't want to deal with, if possible. They're hard to use because, well, they're not necessarily always compatible with out-of-the-box software. And they're hard to use for the more fundamental and, well, frankly, disappointing reason that people don't really like to think hard every time they do things. And so, if you've got some definition that makes you think before you do anything, then it's going to run into inherent resistance, right? So several systems, there are a lot of systems that have been developed to make it much easier to use. Frank McSherry had something called Pink, which is a query language, kind of like SQL, except it's Microsoft's version. It's a group at Penn has, and I'm actually missing a reference here. There's also Anupam Datta at CMU. They've been developing programming languages where differential privacy is actually enforced by the type system. So any program that compiles will be differentially private, in principle. And then there were a couple of systems developed by Roy et al. And Moharan et al., and that's including a student of mine, who developed systems for sort of various restricted classes of queries where their focus was really on the usability of legacy code. Okay, but those systems are actually remarkably usable, but it's still very far from something you can just hand to the statisticians at the census and say, okay, you don't have to think anymore, go use it, right? There is I don't have it on the slide, but there's a product in use at the census that uses differential privacy that was called On the Map. It's an econometric data set. And I was hoping in time for the talk to get some pretty pictures from it, but I didn't. Sorry. But so there are these systems that are out there that make use easier. The disappointing thing is that it's really hard to get these things right. It's really hard to program these systems in a way that's actually differentially private. And there are all sorts of channels that show up that some of which we're used to thinking about, like timing attacks. And some of which we're not used to thinking about, like leakage via numerical errors. So this is a paper of Ilya Mironov that will appear at CCS this year. And so, I would say just as the definitions could be in flux, the algorithms are getting better and changing, so the sort of systems aspect of this area is very much in its adolescence and still on the way to being refined. Okay, so let me here's some things I didn't cover. There are lots of things I didn't cover. Okay, so just wrapping up. So what I've suggested is that if I think of privacy in terms of the effect of individuals' data on the output, this buys me something. It gives me a purchase on this problem. It's meaningful, the way it was described for differential privacy, it's meaningful despite essentially arbitrary external information, and it has this kind of game theoretic interpretation that, well, I should pitch my data in if I get any better. If I know you're going to be using a differentially private algorithm, and I get some benefit out of that, be it like a set of free steak knives or a warm fuzzy feeling from having filled out the census form and followed the law, then I should participate. It leads to this sort of question: well, what can we compute with these rigorous guarantees? I gave you some basic tools, a more advanced example, and I was going to get into more that are drawn my own recent work, but I didn't. Future work, there's a lot to be done. Okay, so I mentioned earlier the fact that the state of the attacks is extremely ad hoc, and we don't really know much. Definitions, we have one. We've got some other candidates. They start getting really hard to compare fast, and unfortunately, because of these sort of inherent trade-offs, it's not likely that we're going to find one that just makes all the problems go away, right? So this is an area where to work in, you're going to have to actually read the definitions and understand them. And as I said earlier, that's an upsetting thing because suddenly people have to think hard, and we all know where that leads. Right. So let me try one. Okay. There's a lot of application areas where differentially private algorithms still suck badly, and one of them is genetics. The data is very sparse, very high dimensional, and very hard to deal with. Another is finance. Finance is interesting for that reason I mentioned earlier, that there are other considerations at play other than individual privacy. Okay, so what I hope you got out of this talk is this sense that privacy is hard to reason about. A, it is possible to reason about. B, and there's lots of interesting work to be done. Further resources, Aaron Roth at Penn has this nice set of lecture notes on his course from a course that he taught last fall. Sofia Rashodnikova and I at Penn State have some course notes that are older and frankly less polished. And there's a DIMAX workshop on data privacy that'll be coming up right immediately after Fox at Rutgers, which Fox is also at Rutgers, so that'll be the Wednesday, Thursday, Friday right after Fox. So if you're in the New York area or if you're going to Fox, please consider attending. It should be a very interesting workshop. I'll just stop there. Thank you very much.